Hello everyone. The headline of this tutorial is continuous function. Listen to 4. Definition. A function f is said to be continuous at a point c x equals c if the following conditions are satisfied. 1. The function is defined at x equals c. 2. The limit of the function exists when x approaches to c. 3. The limit of the function when x approaches to c equal to f of c. If at least one condition is not met, then the function is not continuous. The function f is discontinuous at this point if it is not continuous. In certain cases, you can redefine a discontinuous function at x equals c to remove the discontinuity. At this point, in this case, we say that the discontinuity is removable. Example. Use the given graph to discuss the continuity of the function at x equals c. Number 1, c equals -2. Use this graph to discuss the continuity of this function when c equals -2. The first condition is f of -2 exists. F of -2 here is -2. So f of -2 equal to -2 exists. The first condition is made. The second condition, the limit of the function when x approaches to -2 exists. When x approaches to -2 from right, the function goes to -2. When x approaches to -2 from left, also the function goes to -2. So the limit of f of x when x approaches to -2 from left and right is -2 and exists. 3. The value of the function at -2 equal to the limit of the function when x approaches to -2. So this function is continuous when c equals -2. Number 2. Use this graph to discuss the continuity of the function when c equals 3. The first condition, f of 3 should exist. F of 3 here is 1. The limit of the function when x approaches to 3 should exist. The limit of the function when x approaches to 3 from right is 0 and from left also is 0. Then the limit is 0. But the third condition, f of 3 is not equal to the limit of f of x when x approaches to 3. Then this function is discontinuous. This function is continuous. Number 3, discuss the continuity of this function when c equals 2. When c equals -2. Sorry. When c equals -2, the value of the function is 3. So f of -2 is 3, as you see here. The limit of the function when x approaches to -2 equal to, when x approaches to -2 from right, the function goes to 2. And from left, also the function goes to 2. Then the limit is 2. But the value of the function at -2 not equal to the limit of the function when x approaches to 2, then the function is discontinuous when c equals -2. 2, not equal to the limit of f of x when x approach to negative 2. So discontinuous. C equals 0. This is 0. F of 0, as you see, is 0. F of 0 is 0. The limit when x approach to 0 from left and right, the function is, for the function is 0 when x approach to 0. And the value of the function at 0 equal to the limit of the function when x approach to 0. So the function is continuous when c equal 0. Number 4, use this graph to discuss the continuity of the function when c equal 4. This is 4. F of 4 is 2. The first condition exists. F of 4 equal 2. The limit of the function when x approach to 4 from right is 2. Is 2. The limit of the function when x approach to 4 from left, the function is negative 2. So the limit does not exist and the function is not continuous because the second condition is not met. Number 5, use the graph to discuss the continuity of this function when c equals to negative 1. This is negative 1. F of negative 1 is 0. The first condition, f of negative 1 equals 0. Limit of f of x when x approach to negative 1 is, when x approach to negative 1 from right is 0, not equal to the limit when x approach to negative 1 from left for f of x. Because when x approach to negative 1 from left, the function approach to 2. Therefore, the function is not continuous because the third condition is not met. Definition. The greatest integer function, symbolized by x between two brackets of this kind of brackets, is defined as the largest integer less than or equal to x. Less than or equal to x. For example, f of x equal greatest integer of x. If we want to find f of negative 2, then the greatest integer of negative 2 is negative 2. F of 3 also is 3. F of 2.9, the greatest integer less than or equal to 2.9 is 2. Then the value of f of 2.9 is 2. F of 2.1, the greatest integer for 2.1 less than or equal to 2.1 is 2. F of negative 1.6, the greatest integer to negative 1.6 is negative 2. It is not negative 1 because negative 1 is greater than negative 1.6, but negative 2 is less than negative 1.6. Also, f of negative 1.2, the greatest integer of negative 1.2 is negative 2 because negative 2 is less than negative 1.2, but negative 1 is greater than negative 1.2. For the limit of the greatest integer function, x is for any non-integer number a. If a is not non-integer, then the limit of the greatest integer x when x approach to a is the greatest integer of a. For any integer number a, then the limit from right for the greatest integer x equal to greatest integer of a. But the limit when x approach to a from left is for greatest integer function of x is greatest integer of a minus 1. Example, discuss the continuity of the function 1/2 greatest integer of x plus x. This function has discontinuous point when x is integer and continuous function continuity when and has continuity when x is non-integer function point. For example, if we want to discuss the continuity when x equal to 2, then f of 2, the first condition, is 1/2 greatest integer of 2 plus 2 equal to 1/2 greatest integer of 2 is 2 plus 2 equal to 3. Limit x approach to 2 from right to the function 1/2 greatest integer of 2 plus 2 equal to 1/2 when x approach to the integer number from right is greatest integer of the number. Greatest integer of 2 is 2 plus 2 equal to 3. And the limit when x approach to 2 from left to this function is 1/2 2 plus 2 equal to 1/2 greatest integer of a minus 1. So I will write minus 1 plus 2 here. Greatest integer of 2 is 2 minus 1 plus 2 equal to 1/2 times 2, 1, 1 minus 1, 0 plus 2, 2. Since the limit from right is not equal to the limit from left to this function, then the limit is not exist. And the second condition of continuity conditions is not met. Then the function is not continuous when c equal integer number. If we take a negative integer number, also we find that f of -3 equal to 1/2 greatest integer of -3 plus minus 3 equal to -3 over 2 minus 3 equal to -4.5. Negative 1.5 minus 3, -4.5. Limit when x approach to -3 from left, from right first, is of this function is equal to 1/2 greatest integer of -3 minus 3 equal to -4.5. But the limit when x approach to -3 from left for f of x equal to 1/2 greatest integer of negative 3 minus 1 minus 3 equal to negative 5.5, and since the limit from right not equal to the limit from left, the limit does not exist and the function is not continuous at the integer positive or negative. If we discuss the continuity of the greatest integer at non-integer number, for example 2.5, then f of 2.5 equal to 1 half greatest integer to 2.5 plus 2.5 equal to 1 half greatest integer of 2.5 is 2 plus 2.5 equal to 3.5. 1 half times 2, 1 plus 2.5 to 3.5. The limit of the function when x approach to 2.5 equal to 1 half greatest integer of 2.5 plus 2.5. When for any non-integer, in general, when x approach to a, for greatest integer a is greatest integer of a equal to 1 half times 2 plus 2.5 equal to 3.5, and f of 2.5 equal to the limit of f of x when x approach to 2.5 and the function is continuous. Example, determine whether the following functions are continuous or not at the given points. F of x equal to x power 2 minus 2x plus 1 when x equals c. c is any real number. F of c, the first condition, equal to c squared minus 2c plus 1. Limit of f of x when x approach to c equal to c squared minus 2c plus 1. Since the value of the function equal to the limit of the function when x approach to c, then the function is continuous when x equal any real number. F of x equal 5 when x equal 3, or we can write x equal c also. F of c equal 5, limit x approach to c for 5 also equal 5, and f of c equal, f of 5 equal to the limit of the function when x approach to c and equal to 5, then the function is continuous. F of x equal absolute value x minus 1 when x equal 8 and x equal 1. F of 8 equal to 8 minus 1 absolute value equal to 7. Limit x approach to 8 for f of x also equal 8 minus 1 absolute value equal to 7, since f of 8 equal to the limit of the function when x approach to 8, then the function is continuous. When x equal 1, f of 1 equal to absolute value 1 minus 1 equal to 0. Limit for f of x when x approach to 1, also 1 minus 1, absolute value equal to 0, and the value of the function at 1 equal to the limit of the function when x approach to 1, and the function is continuous. Notes. The first note, The polynomial function, this function, are always continuous. The polynomial functions are always continuous in its domain. Whenever you see polynomial function, then this function is continuous everywhere because its domain is R, all real number. Also, the constant functions always continuous because the constant function is polynomial of degree 0. Therefore, the constant function, its domain is R and always is continuous at all real number. If the function, any function, polynomial or not polynomial, has a domain equal to R or real number, then it is continuous everywhere. For example, f of x equal 1 over 2 plus x squared. The domain of this function is R since there is no point make the denominator 0. If we solve 2 plus x squared equals 0, then x squared equal to negative 2, then x equal to negative positive square root negative 2, not a real number. Therefore, there is no value make the denominator 0 and the domain is all real number, then this function is continuous everywhere. Also, f of x equals sine x, since the domain of the sine and cosine is all real number, then these functions are continuous everywhere. Number 7, f of x equal to square root x power 2 plus 1. The domain of this function is all real number because I have x squared here. If I take negative number, by the square would be positive, and therefore the domain of this function is all real number and it is continuous everywhere. Also, the cube function of the cube root of x minus 1, its domain is all real number. Therefore, this function is continuous also everywhere. Example, discuss the continuity of this function at x equals 0 and x equals 1. At x equals 0, f of 0 equal to 0 over 0 square minus 0 equal to 0 over 0 and defined. Therefore, the first condition of continuity conditions is not met and the function is discontinuous at 0. For x equal 1, f of 1 equal to 1 over 1 minus 1, 1 square minus 1 equal to 1 over 0 also is undefined, and the function is discontinuous at 1 because it is the first condition is not met. But we will see later here that the function has a removable discontinuity at x equals 0, since the limit when x approaches 0 for this function, x over x squared minus x equal to limit x approaches 0, x over x, x minus 1, reduce x with x, substitute every x with 0, then the limit is 1 over 0 minus 1, negative 1, equal negative 1. Since the limit exists when x approaches to 0, then this function has a removable discontinuity at 0, but has a non-removable discontinuity when x approaches to 1, because 1 minus 1 make the denominator 0. Anyway, note, the function f of x has a removable discontinuity point x equals c if the limit of the function when x approaches to c exists. For example, discuss the continuity removable or not removable of the function f of x equal absolute value x minus 3 over x minus 3 when x equal 3. F of 3 equal to 3 minus 3 absolute value over 3 minus 3 equal to 0 over 0 undefined, and the function is discontinuous because the first condition is not satisfied. If you want to find the removability of this function at x equal 3, then we need to find the limit when x approach to 3 for this function. And to find the limit, we should remove the absolute value equal to x minus 3 when x greater than or equal to 3 and negative x minus 3 when x less than 3. And we take the limit when x approach to 3 from left. From left, it means the absolute value equal negative x minus 3 over x minus 3. Reduce x minus 3 with x minus 3, the answer is negative 1. And the limit when x approach to 3 from right, the absolute value x minus 3 equal to x minus 3. X minus 3 with x minus 3, the answer is 1. Since the limit is not exist, then the discontinuity of this function at x equal to 3 is not removable. Question number 2 also discuss the continuity, removable or not removable of this function at x equal 1. F of 1 equal to 1 square minus 1 over 1 minus 1, 0 over 0, undefined. The function is not continuous because the first condition not satisfied. But the limit when x approach to 1 for this function is equal to limit x approach to 1 and analyze difference of 2 square for the numerator and reduce x minus 1 with x minus 1, substitute every x with 1, 1 plus 1, 2. Since the limit exists, then the discontinuity of this function at x equal 1 is removable. And we can redefine this function as f of x equal to piecewise function x squared minus 1 over x minus 1 when x not equal to 1, 2 when x equal to 1. Now f of 1 is 2, the limit also is 2, the value of the function equal to the limit of the function when x approach to 1, and the function is continuous. Which of the following has a removable discontinuity at x equals 0? We will find the limit of this function at x equal to 0 to know which one has a removable discontinuity. For the first one, the limit when x approach to 0, 1 minus x over x squared equal to 1 minus 0 over 0, 1 over 0, it is undefined. The limit not exists, so this choice is wrong. For the second function, limit x approach 0 for x squared minus 3x over 2x. Factorize x approach 0, factorize the numerator by x minus 3 over 2x, reduce x with x, substitute every x with 0, 0 minus 3 over 2, negative 3 over 2, the limit exists, and the right choice is B. But let us find the limit of this function. Limit cosine 3x over x when x approaches 0 is cosine 3 times 0, cosine 0, 1 over 0, undefined. And for the last one, the limit when x approaches 0 for x minus 1 square over x square, x minus 1, reduce x with x minus 1 with x minus 1. The answer will be x minus 1 over x when x approach 0. Substitute every x with 0, negative 1 over 0. It is undefined. Therefore, the right choice is B. Example, which of the following has an unremovable discontinuity at x equal 2? An unremovable discontinuity, it means the limit not exist at x equal 2. Let us see the limit of this function when x approaches to 2. Analyze difference of two by experiment x, positive, negative, 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 2, 1 over. Even analyze the denominator difference of 2 square, x minus 2, x plus 2. Reduce x minus 2 with x minus 2, substitute every x with 2. The answer will be 2 minus 1, 1, 2 plus 2, 4. The limit exists. This discontinuity is removable, so it is not the right choice. For the second function, limit x approach 2, analyze the numerator difference of 2 cube, x minus 2, x power 2, reverse sign, the first one times the second one, 2x plus 4 over x minus 2 all square. Reduce x minus 2 with x minus 2, substitute every x with 2, 2 power 2, 4, plus 2 times 2, 4, plus 4 over 2, minus 2, 0, then this discontinuity is not removable because the limit is not exist. The right choice is B. Let us continue. The third function, the limit when x approach to 2 minus x, factorized by 3, by negative 3, 2 minus x, negative 3 times 2, negative 6, negative 3 times negative x, 3x, 2 minus x with 2 minus x, substitute every x with 2, there is no, it is constant function, negative 1 over 3. So also this discontinuity is removable. For the last function, limit x approach 2, difference of 2 square for the numerator, x minus 2, x plus 2, analyze by experiment for the denominator, x, negative, negative, positive, negative, 2, 1, x minus 2 with x minus 2, substitute every x with 2, 2 plus 2, 4, over 2 plus 1, 3. Also, this discontinuity is removable because the limit exists, but the second function is not removable because the limit is not exist. See you next lesson.